So today we are going to study directed polymer on trees. Okay, so it's a bit of a misnomer because I think most of what I'm going to say was proved much before directed polymers were invented. But yeah, an alternative name can be multiplicative cascade. Okay, so the idea is that we are going to consider T, okay, which is TD, which is, okay, the D regular oriented tree. Okay, I don't know if this is a good name or not, but okay, what is it? Well, it's simply a tree, okay, where every vertex has 3 D, sorry, and D can be equal to 3, as D children, okay, so, and so on. Okay. So, yeah, so what's an element of T? Well, it's just is a word. Okay, so a finite word in the alphabet 1 to D. Okay, so what I mean is just, yeah, this is a list of symbols, okay, and you just take a finite number of them and put them together in some order, and this gives you a word, and this is how you encode your tree. So this vertex here, it's the empty word. Okay, this is 1, this is 2, this is 3, this is 1, 2, this is 1, this is 1, 1, 1, 2, 1, 3, etc. Okay. So another way to write that is that T is just, well, the disjoint union of 1D to the N. Okay, and okay, so yeah, I write this product symbol reverted. And yeah, this is kind of the symbol for disjoint union as an operation. Okay? Like if you write this, it means that the AI, you already know that they are subsets of something and that they are disjoint. Here it's somehow, I mean, like, okay. For instance, you can define this. Okay, it's just a disjoint union of something with itself. It's just the algebraic construction. You say, okay, I have 2 copies. I put them together, and I will either. Okay, so this is the difference between these 2 symbols. Okay, here you can glue things that are non-related to each other, and you can glue several copies of the same thing if you want. Okay, and for V in P, in T, sorry. Let me call this T without a double bar. For V in T, if V belongs to 1D to the N, we say that the length of V, and I write it with bars, is equal to N. Okay, and finally, if v equal n and k is smaller than n, vk is the, well, denotes the k truncation of v. Okay, so just I keep the first k letters of v, and okay, so are all the notations clear? Okay, so now, okay, and somehow, okay, this thing here, if I consider this as a subset of T, okay, I will just call this Tn. Okay, Tn is just the nth generation of my tree T. Okay, so we let omega v, v in T, be an IID collection of random variables. And we are going to take the usual assumptions. So they have and okay, I'll assume that they are normalized in the following manner. Okay, centered and with unit variance. Okay, and I'm going to define for v in T, I define h omega v. It's the sum from n equal 1 to v of omega v. I will just forget about the minus for today, just to avoid confusion. Okay, and finally, I'm going to define my polymer model on the tree. Well, it's going to be a measure, a sequence of measure on T capital N. Okay, and well, it will be the model will be associated with the partition function Zn, okay, which is just the sum over V in Tn of exponential minus beta and I don't put a minus. Okay, and P and beta omega V is equal to 1 over Zn beta omega exponential minus beta h. Okay, so you might think it's a bit different. Before on ZD we had a measure on paths. This time we have a measure on a set of vertices. But on the tree, on a directed tree, a directed path of length n and a vertex, it's the same thing. Okay. Yeah, what we have, okay, let me take n equal 2. You have really a measure on this set of vertices, but like really you can think that each vertex is a path, okay? You can identify a vertex with a path which is linking this vertex to the root. Because we don't have a minus here, so we don't have a minus there. Just so that I don't get confused. It doesn't seem to be working, but this is an attempt of. Okay. I'm going to say some things about H today, and if I put a minus, I will probably forget about it later. So. Okay, and somehow we are going to say things about Zn directly, but it's also important to look at the renormalized version. So Wn beta omega. Okay, it's just okay, and it's the same thing as before. I'm just dividing by the number of terms in my sum, which is just d to the power n. I'm summing over Tn, and here I'm taking exponential beta h omega v minus lambda beta. Okay, and you see that this has expectation 1. Okay, and you can check that if you look at the expectation of Wn plus 1, knowing Fn, where Fn is sigma of omega v, v less than n. Well, this is equal to 1 over d to the power n plus 1, sum over v in t n plus 1. Okay. Which is equal to, okay, here I can just decompose this thing into 2. So I can say this is exponential beta h v n. I'm just taking the immediate ancestor of v here. Okay. Here I don't have a plus, I have a minus, and here I have n plus 1. Okay, then I have this. Okay, this is equal to 1. Okay, and here I'm counting d times each vertex on generation n. So this is equal to Wn. Okay, so for this is very similar to the model on ZD. We have a martingale property for Wn. Okay, and yeah, what I want to do today is basically okay, I will probably finish tomorrow. Is to compute the free energy for this model. Okay, and we are also going to show that basically for this model you either have weak disorder or very strong disorder. Okay, so either the free energy will be negative, or Wn will converge to a non-zero limit, except at the critical point, okay, where you have strong disorder. Okay, so this factor on the tree is well, it's somehow important because it led people to make the okay. some people to write the wrong conjecture about what should happen on ZD. Okay, so on ZD you have weak disorder at beta C. Okay, on the tree you have strong disorder at beta C. Okay, so let's call G beta, which is the limit when n goes to infinity of 1 over n log z and beta omega. Okay, somehow, if you want, you can prove the concentration result for this. Somehow, in the theorem, we will prove that the limit exists. We will prove we will get the exact value of G beta, and as a consequence, we'll get the existence. Okay, so. Okay, and I will define beta C, okay, as the infimum of beta such that beta lambda prime, beta minus beta, minus lambda with beta is larger than log D. Okay, so lemma beta C is finite if and only if the probability that omega is equal to its essential supremum is larger than 1 over t. Okay, so we are going to prove that this is the critical point, okay, for the phase transition. But just before, I just want to tell you that this thing is okay. This thing it's well defined, okay. It's positive, okay, with no loss of generality. I mean, here you have a continuous function that starts from 0. You want it to be above a certain threshold, you know you have an explicit condition for it to be finite. Okay, so proof. Okay, so first something which is perhaps not necessary for the proof, but this thing here, okay, it's an increasing function. Okay, so therefore, basically, once you cross this threshold, this thing is true. Okay, so beta lambda prime beta minus lambda beta prime, it's equal to lambda prime beta, which is positive. Okay, we have proved that this is a convex function. Okay, and you can compute the variance. This thing is really the variance of something, so this is strictly positive. Okay, so okay, and another remark is the following. Oh, what? Yes. This. Okay, sorry. Okay, and the other thing you can say is that if you look at this, lambda prime of beta, well, because of convexity, you can squeeze it between two things. So you can say it's smaller than lambda 2 beta minus lambda beta over beta. Okay, this is the slope between 2 beta and beta. And this is larger than lambda beta minus lambda beta over 2 divided by beta over 2. Okay, again, this is the slope between these 2 points. Okay, so now can write what this gives me for lambda prime beta, beta minus lambda beta. Well, this thing, it's smaller than lambda 2 beta minus 2 lambda beta, and it's larger than lambda beta minus 2 lambda beta over 2. Okay, and now we have shown, okay, we know that the limit when u goes to infinity of lambda 2 beta minus 2 lambda beta, it's equal to minus log p omega equal to m. Okay, where this m here is the essential supremum. Okay, this is something we have seen when we have computed second moments, if you remember. Okay, and here you see, therefore, that well, you can apply the sandwich theorem for limits. Okay, to see that this has to converge to the same thing. Okay, so therefore you see that the limit when beta goes to infinity of beta lambda prime beta minus lambda beta is equal to minus log probability and okay, you get this. Okay, this was in the wrong direction. Okay, so for instance, if you take unbounded environments or environment with density or environment with no atoms, you know that beta c is infinite. Beta c is finite. Okay, so in all these cases, okay, so unless you take something very specific, you have a phase transition, and the expression for the free energy is the following. This is a theorem. Okay, and I would say most of it is due to Kahn and Perrier. So from 74. This paper, it has two particular things about it. First, it's written in French. When I read it, it took me like several days to realize that there was something special about that paper. I couldn't do it, but it's in French. Perhaps you would have been faster than me to find this out. The other thing is that the authors, they kind of underline in the paper who did what, which is a bit unusual, but perhaps it was customary in the 70s, I don't know. So perhaps if you read that paper, you will know if the theorem is due to Kahn or Perrier. Okay, and what the theorem says is that, well, G of beta, it's equal to log D plus lambda beta if beta is smaller or equal to beta c. And it's equal to lambda prime beta c times beta, I guess, if beta is larger than beta c. Okay, to check if this is right, basically you have to check continuity. And this is good, right? At beta c, the two things are equal. Okay, so, and the other thing, okay, which is probably if beta is smaller than beta c, then W, the limit when n goes to infinity, is positive, almost surely. Okay, and okay, so weak disorder below beta c, strong disorder. Okay, these things basically, it's not. I didn't call it F, but if you add F, basically you would just subtract this. Okay. Yeah. So weak disorder below beta c, strong disorder above beta c. Very strong disorder above beta c, strong disorder at criticality. And if you look at the free energy curve, okay, it's something which is quite simple. You have your log d here, and it does something like this. Okay. Okay, so it's strictly convex, and then at beta c, it starts to grow linearly. Okay, so before proving this result, let's try to see what this thing means. Okay, and to understand what's going on there. Okay, so the first thing we can show as a corollary okay, so let's call H max, well, okay, H and max of omega, well, it's equal to the maximum over V in Tn of H V omega. Okay, and a corollary we have here is that the limit when n goes to infinity of H n max omega divided by n, well, it's equal to lambda prime beta c. Okay, so this is corollary 1. So how do you prove it? Well, basically, you know that the n beta, okay, well, this thing, it's smaller than, well, exponential beta h n max times d to the power n. Okay, and you know that it's larger than exponential beta h n max. Okay, so what you get out of it is the following. You get, okay, you divide by n, take the log, take the limit, so you get that g beta. It's smaller than log d plus beta lim inf of 1 over n h n max. And it's larger than beta lim sup 1 over n h n max. Okay, and well, you make beta tend to infinity. Okay, and you get that the limit of 1 over n h n max, well, it's equal to the limit when beta goes to infinity of g beta divided by beta, which is equal to lambda prime of beta c. Okay, so something, okay, so there are other ways to get this. Somehow, here's the upper bound. You can get it in a rather trivial manner, just by saying, well, the probability that the max is larger than this is the probability that there exists one path which is larger than this, and it's smaller than d to the power n times the probability that a specific path is larger than this. Okay, and basically here you can do the union bound and it's sharp. Okay, and if you want things in the other direction, you can do second moment. But I think what is interesting about this result is really the fact that okay, this inequality here is an equality as soon as beta is larger than beta c. Okay, here you do not take only the limit. I mean, like this is an equality as soon as beta is larger than beta c. Okay, so what this indicates, and you can go further, is that when you go past the threshold beta c, okay, basically your measure is essentially supported by path that maximizes the energy. Okay, so I will now give you a second corollary that goes a bit further in that direction. Any question? Corollary 2. So you have two things here. So first thing is P and beta omega of H V. Okay, here V is a random variable associated with this probability. Okay, you're sampling V at random. The probability is that HV minus n lambda prime beta is larger than n to the alpha. Okay, this is, okay, this goes to 0. Okay, and the second thing, this is if beta is smaller than beta c. Okay, and the second thing is, well, the limit when n goes to infinity of the probability that HV is larger than lambda prime. Okay, smaller than lambda prime beta c minus delta times n. This is equal to 0 if beta is larger than beta c. Sorry? Yes?
How are you?
Beta c has also no dependency on beta. Yeah, basically, but beta c is something which is determined by two things, basically by D and the distribution of the Auroral environment. Okay, so yes, how is this proved? Well, okay, this is. Okay, so let's start with A. And then we will kind of deduce B from A. So for A, basically, yeah, we want to use this. Okay, so what we are going to prove is that the limit when n goes to infinity of Wn beta omega Pn beta omega HV minus n lambda prime beta is larger than n to the alpha equal to 0. And to prove that this goes to 0, we are going to prove that the expectation goes to 0. Okay, why is this equivalent to that? Well, this thing, we know that it converges to a positive random variable. Okay, so if the product converges to 0, this means that the second term converges to 0. Okay. Now, what's the expectation of this? Well, this is equal to 1 over n d to the power n sum over v in Tn. Okay, I'm using Fubini here directly. And here I will get the expectation of exponential beta hv omega indicator then that h omega v minus n lambda prime beta is smaller than n to the alpha, larger than n to the alpha. Did I mention that alpha was larger than 1/2? Alpha is larger than. Okay, so now basically here you have a sum of IID random variables. Okay, and here as well. So this thing does not really depend on the V you choose here. So you can just look at this and you can say, okay, it's just expectation of exponential beta Sn indicator Sn minus n lambda prime beta larger than n to the alpha. Okay, where Sn it's equal to the sum from n equal 1 to n of omega n. Okay, where omega n, they are just IID random variable with the same distribution as omega empty set as your omega v's. Okay, and this last thing you can just write it as okay, where here okay, dp beta over dp, it's equal to exponential beta Sn minus lambda beta. Okay, and did I put, I forgot, yeah, I forgot about the lambda beta here, which is important. Minus n lambda beta. And here you have an n as well. Okay? The thing we have here, okay, because it has expectation 1, it's a probability density. So the important thing is that under this probability, our omegas are IID. Okay, so under p beta omega n and 1 to n are IID. Okay, the expectation is equal to lambda prime beta c, lambda prime beta. Okay, and the variance and omega n's, omega 1 has finite exponential moments. So in particular, it has finite variance. Okay, so therefore you get that, you know, that this probability here, okay, it's smaller than exponential minus, okay, minus c n to the 2 alpha minus 1. Okay, using the usual large deviation trick. Okay, I mean, you can use Chebyshev if you want, but just if you want to get almost sure convergence, okay, this is a way to have Borel-Cantelli for cheap. Okay, just let's take a small break and resume in 5 minutes for the second part of the program. avoid this order phase. Then what trajectories are doing is that basically you're trying to find energies of that level, okay? And you can say a bit more actually, because here, the event you could put here could be any event, and basically you can say, okay, what I want is that the energy profile is similar to what I would have with IID, sum of IID random variables distributed with this tilted distribution. Okay, so for instance, you might be able to say, okay, basically, what I will see is not only something with this, but I know that the fluctuation around will be of order square root of n. Okay, and I know that before getting there, basically, I will have a kind of a Brownian fluctuation, okay, around this mean. Okay, if I look at the genealogy of V, and if I look at the evolution of the energy, okay, if I look at h of Vn, n equal 1 to n, okay, this thing is going to typically look like a random walk with this distribution. Okay, and what happened is that basically, yeah, the set of vertices that satisfies this, okay, it gets thinner and thinner when beta gets larger. Okay, basically, the set of vertices at generation n that satisfies this, it's like a power of n. No, it's a power of n. No, it's an exponential. It's exponential in n, but it grows smaller than d to the power n. Okay, it grows like a function of beta to the power n, and this function of beta, okay, at 0 it's equal to d, then it decreases, and then at some point it reaches 1. Okay, and then somehow the system freezes, and you're basically stuck with well, what's left, things with highest possible energies. Okay, so for the second point, there is not so much to prove, in fact. You just have to show some kind of monotonicity statement in beta, and then you can deduce things from A. Okay, so for B, well, okay, you can look, okay, that okay, you can compute this explicitly, and this thing is equal to, okay, E and beta omega yeah, HV indicator, HV larger than U. Is it so? Perhaps. Let me check. Yes, I think you get HV minus lambda prime beta here. Minus n. Minus E and beta omega HV minus lambda prime beta times P and beta omega HV is larger than U. Okay, and this is larger than 0. Okay, just because this is an increasing function of this is an increasing function of Yes. This is an increasing function of hv. This is an increasing function of hv. So it's just positive correlation of increasing functions. Okay. This is just this. Fg g mu is larger than f t mu g g mu. Harris inequality in dimension 1, like the easy one. Okay, where here mu is just a distribution of hv. Okay, so this is, okay. So in particular, okay, here it's sufficient to have this inequality for beta, for some beta, which is some beta prime, which is smaller than beta. Okay, so take beta prime, which is smaller than beta c, such that lambda prime, beta prime, okay, is equal to lambda prime beta c minus delta over 2. Okay, this is always possible if delta is sufficiently small. Okay, just because lambda prime of beta, it's a continuous function. And then we have that p and beta omega hv larger than n lambda prime beta minus delta. Well, this thing, it's larger than p and beta bar omega hv larger than n lambda prime beta minus delta. Okay, and well, this thing is just you can hv is larger than n lambda bar beta minus delta over 2. Lambda beta bar. Okay, lambda prime beta. Okay, and then you can conclude with okay, so yeah, let me comment. This kind of behavior, this freezing behavior, it's really specific to the tree, and it's not this doesn't happen for ZD. Okay, basically, even in the very strong disorder phase on ZD, basically the typical energy you find it continues to lower with beta. Okay, and the specific thing on the tree is that when two paths separate, they cannot go back together. And this makes this freezing phenomenon happen. Okay. Okay. So I think. Well, any question about this? Okay. So this makes us ready to prove this statement. Okay, so the first thing we are going to prove is that weak disorder holds if beta is smaller than beta c, and then if we have time, we will prove the strong disorder part. Okay, and the proof is something almost that we have already seen. Okay, basically we are going to use. Okay, so to prove weak disorder on ZD, we used second moment method. Okay, and I said it wasn't sharp. Well, second moment method is not sharp here, but what we can do is twist it a little bit and use it to estimate moments of order between 1 and 2. Okay, and then it gets sharper and sharper when you get close to 1. And this is what will allow us to conclude. Okay, and On the other hand, for strong disorder, what we will do is the same thing. We will try to estimate moments, but of order this time between 0 and 1. And basically, we'll get a criterion which gets sharper and sharper when the moments we consider are of order close to 1. And yes, the good thing is that the two things we are considering, I mean, the two criterion, they will match when you get from one. I mean, the techniques will be different, but you will get the same criterion when you consider moments of order 1 going from above or going from below. Because this is what makes this possible. OK. So beta smaller than beta c implies that our infinity is positive or natural. Okay, so yeah, so let me first. So what we are going to show really is that the supremum over n of wn to the p is finite for some p larger than 1. Okay, so this implies in particular that wn beta is uniformly integrable and hence converges in L1. So this thing is to give you that the expectation of W infinity is equal to 1. You don't lose mass in the limit, and therefore the limit cannot be trivial. Okay? The fact that you have convergence is really a direct consequence of the fact that your process is a non-negative martingale. Okay, then you need the 0-1 law. Okay, and somehow the 0-1 law, it will be the consequence of an identity, which we are going to use for this proof. So let me try to write this. Okay, so let me decompose Wn into a sum. So what I want to say is that Wn, well, okay, it's a sum over the tree, and what you can do is, well, it's decompose this sum into a sum over the first branch, a sum over the second branch, and a sum over the dth branch. So, okay, so let me write it as Wn plus 1. Okay. So when you're summing over the first branch, what you will get is, well, 1 over d exponential beta omega 1 minus lambda beta. Okay, and then you will get something which is W, which I will call Wn1. And Wn1, okay, by definition, okay, so I call Tm1, it's the set of V's in Tn such that V1 is equal to 1. Okay, perhaps let me put an I here and I here. Tn plus 1. Okay, I'm just what I'm just saying. I'm saying that this thing here I can somehow identify it with a copy of Tn. Okay, this is the reason why we have this. Okay, and W and I, it's just, well, 1 over d to the power n, sum over t and I, exponential h v omega minus beta omega I, okay, minus n lambda beta. Okay, the important thing is that this thing is equal in distribution to Wn. Okay, what I'm doing is just taking the same thing as before, except that I'm just ignoring the root, because this is what you want to do. Okay, and because I'm summing over the nth generation of a tree of height n, I'm doing just exactly the same thing as before. Okay, so okay, so in particular, what I have is that W infinity is equal to the sum over I equal 1 to d. 1 over d exponential beta omega I minus lambda beta omega infinity I. Okay, so this equality in distribution is not only for a marginal, but it's also true for a process if you consider this as a process indexed by n. Okay, because this thing it's like the family of growing trees. I mean, like these are exactly the same thing except that you are considering shifted trees. Okay, if you remember well, this thing is exactly the identity with the shift that we had written. Okay, and well, the result of this is that if you call P is the probability that W infinity is equal to 0, okay, what you get is that P is equal to P to the power D. Okay? This is equal to 0 if and only if all of these things are equal to 0, and now all of these things are independent. Okay, so this implies that P belongs to 0, 1. Okay, so now let's prove this. Let's prove this, and I'm just going to fix P between 1 and 2, okay? And we are going to decide later the value of P. Okay, I don't exclude 1 and 2, but okay, in the end, I'm going to really choose something which is within this interval. Okay, so what is the expectation of W n plus 1 to the P? Well, okay, I want to prove an upper bound. So what would be nice would be to use subadditivity. Okay, subadditivity is true when you have exponents that are smaller than 1. So what we are going to do is to make P smaller than 1. So 2 to the power p over 2. Okay? So, and now we are going to expand the square. Okay, so here we have a square. The square is a sum. We are going to expand the square and then use subadditivity. Okay, so this is equal to the expectation of the sum I equal 1 to d, sum, okay, this is smaller, j equal 1 to d. Okay, this is equal to this, and this is smaller than sum I equal 1 to d, sum j equal 1 to d, time the expectation of whatever to the power p over 2. Okay, here I'm just using the fact that because p over 2 is smaller than 1, the sum to the power p over 2 is smaller than the sum of the terms to the power p over 2. Okay, and now the reason the reason why I didn't want to write all terms is that basically I need only to consider two kinds of terms here by symmetry. Either I is equal to j or I is not equal to j. Okay, so this last thing here, okay, I have basically d diagonal terms. Okay, and each of them gives me 1 over d to the power p. Okay, 1 over d to the power p over 2 squared. And then I get the expectation of exponential beta omega 1 minus, beta p omega 1 minus p lambda beta omega n 1 to the power p. Okay, and then I get a second term, which is d minus 1. Okay, I get again d to the minus p. And then I get the expectation of exponential beta. Here I get beta p over 2 omega 1 plus omega 2. And then I get omega n 1 omega n 2 to the power p over 2. And then here I get minus p over 2 minus p lambda beta. Okay, so I don't really care about this second term. Okay, because this is smaller than. Okay, I want to show that things are finite, and I want to show that things that don't grow. So here, these things won't be a problem because, okay, here I can always use Jensen and put p over 2 outside. Okay, and when I do this, what I get inside is 1. Okay, because the expectation of this is 1, the expectation of this is 1. These two things are independent, so they don't interact. And these two things are independent, they don't interact. So if I just put p over 2 outside, okay, so it's, okay, this is smaller than here I put 2. P over 2, and then these things become equal to 1. So I don't really care about that. Okay, so what I care about is the other part. So what we get is that the expectation of Wn plus 1 to the power p, well, it is smaller than d to the power 1 minus p, and then I get the expectation of so this first thing, I can write it explicitly. It's exponential lambda p beta minus p lambda beta. Okay. And the second thing is expectation Wn to the p and then plus d1 minus p g minus 1. I don't really care. Okay, so what do I have here? I have a linear inequality. So just by ground rule, okay, if I want to show that things do not grow exponentially, I just have to check that this is smaller than 1. Okay, so we get that the soup of if d to the 1 minus p exponential lambda p beta minus p lambda beta is strictly smaller than 1. Okay, so this condition gives us, okay, so I'll just be looking at the log. So I want the log to be smaller than 0, so this is really 1 minus p log d plus lambda p beta minus p lambda beta. Okay? This thing, okay, it's equal to 0 when beta is equal to 0. So, well, if I want this to be negative at some point, it's sufficient to check the derivative at 0. When okay, it's equal to 0. So it's equal to 0 when p is equal to 1. It's equal to 0 when p equal to 1. Okay? So if I want this to be negative for some p larger than 1, I just have to check that the derivative at 1 is negative. Okay, so we differentiate in p. And we want this. There exists p larger than 1. We differentiate in p, and what we obtain is, well, minus log d plus lambda prime beta. Is it? Yes. Plus beta lambda prime beta minus lambda beta. Okay, and this is exactly equivalent to beta smaller than beta c. Okay, so what makes, okay, this looks really not sharp at first when you do this kind of subadditive thing, but what saves you is that really, yeah, you don't care about the non-diagonal terms. And now if you're considering this sum only with diagonal terms, you know that you have an equality in the other direction, so things should be sharp. Okay, and you see that, yeah, this criterion is strictly sharper than the L2 criterion. In fact, I mean, here you get a criterion for LP boundedness. And this criterion is sharp for all P between 1 and 2. Okay, so what this tells you is that basically, gradually, okay, before losing uniform integrability, you use LP integrability for various P, okay? This P just declines to 1 at some point, and when this critical P reaches 1, basically, you're at the critical point. Okay, so again, this is a contrast with what happened in ZD. In ZD, okay, this is a bit in progress, but what has been clearly underlined in the last years is that basically, yeah, you kind of lose integrability, but the threshold, you cannot go beyond a certain P, which is 1 plus 2 over D. Okay, and then you jump from being in L P for P equal 1 plus 2 over D to not being uniformly integrable. Okay, and again, this is not so surprising. Basically, you can think of things on the tree as infinite dimensional. Okay, so if you're infinite dimensional, then 1 plus 2 over D is equal to 1. So, okay, it's basically the same. Okay, yeah. So these Ds that you have on the tree, it's really not at all the same that what you have on ZD. Okay, like any D regular tree behaves the same. Okay, regardless of this parameter. And it's in a spirit, this corresponds to like very large dimensional behavior. Okay, because in large dimension, basically, two random walk paths, one they separate, they never go back together. Okay. So let's try to do the case B larger than beta C. What I'm going to prove basically is that you have very strong. I'm going to prove that this is an upper bound for the free energy. Okay, so this already gives you very strong disorder. And somehow the lower bound, okay, I won't have the time to detail it, but the lower bound is simply due to convexity. Okay, you have identified the free energy up to there. You know that G beta is convex, so you already know that it's larger than this. Okay, because this is the smallest convex way you can extend the free energy. Sim, para isso que estou tentando ser muito rápido. Não é você que vai defender. Não, tá. Não, estão estressados lá fora? Não, that's going to be quick. Ah, não, você tá participando na defesa? Só vou ligar ali o negócio. Tá. Okay, let's try to do it. So the expectation of Wn. Okay, so we are trying to show that we are G beta. Okay, it's smaller than 1 over the limit when n goes to infinity of 1 over Pn log Wn to the power P. Log Wn to the power P. Okay, just the same thing that we did, remember in DD with, and here we are going to use this for P smaller than 1. Okay, basically, the E is initially outside when you're in the definition of G beta, okay, and here it's Zn. Then you put P there, you're not changing anything, and then you use Jensen. Okay, so now we are going to estimate this, and to estimate this, we are just going to use subadditivity. Okay, P is smaller than 1. Okay, and then we are going to take P to be optimal. Okay, so now E to the this thing. Okay, so by subadditivity, this is smaller than, well, the number of terms you have in the sum times the expectation of exponential, well, sum from n, well, beta p beta Sn. Okay, where Sn it's a sum from n equal 1 to n omega n. Okay, so this is equal to d to the n exponential lambda p beta. Okay, so what we get is that G beta is smaller than 1 over P times log D plus lambda P beta. Okay, and now the next thing we have to do is to optimize over P. Okay, and by magic, we are going to obtain this. So what do? Well, you differentiate and you try to have this thing equal to 0. Okay, so what happens when you differentiate? You get 1 over P square log D minus 1 over P square lambda P beta plus beta lambda prime P beta. And this, you get this over P, right? Not over P squared. Okay, so what you get, at the end, the condition you get is you need to take P such that minus log D minus log lambda P beta minus p beta lambda prime p beta equal to 0, meaning you want p beta to be equal to beta c. So you want p which is equal to beta c over beta, which by chance is smaller than 1, because this is our assumption. Okay, and then all is good. You just replace it, and you get g beta. Well, it's smaller than beta over beta c, no, beta over beta c times log d plus plus lambda beta c. And this thing here, you know that by definition of beta c, this is equal to beta c lambda prime beta c. So you can simplify these things. And we are done. And the defense will be on time. Okay, so perhaps tomorrow I give you more details about how you get the lower bound here, but this is just convexity. Okay, so yes, this is the kind of magic. You do something that looks very stupid, but in the end they are not, simply because here this subadditivity thing, it's kind of sharp when the sum is dominated by the biggest term. Okay, and we have seen, like, but when we have proved this corollary, the freezing property, this is exactly what we have proved.